All right, so today we're going to look at 8.1 Part 2, which is the second part of the law of sines. So we're going to focus more on that side-side angle case. So remember, there's 3 cases that we can do under law of sines. 2 out of 3 of them are pretty straightforward. They just have one set of solutions. When we're solving side-side-side, that's tomorrow. When we're solving side-side angle, that's the one case that you do have to check if there's 2 sets of solutions or no set of solutions. It's the only one that can happen on. Right, so that's what we'll focus on that first, and then we'll finish up with a couple word problems. Right, so I think we'll try to do 4 questions, and that'll pretty much be it. Okay, so here is the information that we're being given. I would make sure that you leave plenty of room in the empty boxes, just in case there's 2 answers. All right, and they asked us to solve. So the first thing you should do is check if this is a law of sines problem, which it is because we don't know any other law yet, or law of cosines. Without sketching it, does anybody remember what you can look for in the table that tells you this is a law of sines problem? Something about the way it's filled out. For example, if you knew a side, and a side, this wouldn't happen. But because you have the information you do, it does happen here. So anybody see what happens in this table when you fill it out compared to if you knew a side, and a side? Yeah?
You can do Pythagorean theorem.
Well, what does Pythagorean theorem apply to? That only applies if you know you have what? Yeah? A 90-degree angle. We don't know we have a 90-degree angle. Maybe we will, but we don't know that yet. So we can't do Pythagorean theorem because that would be assuming one of these already is 90. So we can't do that. But remember, if you have a row that's complete in the table, that tells you that it's a law of sines problem. And you do have a complete row here, A with alpha. If you knew a side, and a side, you wouldn't have a complete row, which means law of sines is not going to work. Okay? But here, it will work. Now, we have a row that's empty, and then we have a partial row. The row that's empty, you need to forget about. There's nothing in that row at all, so you can't do anything with C or gamma, which means we're basically forced to find what first? We don't have any choice. Yeah? Beta. You have to find beta first. So we're going to do this first. Then once you get one angle, well, once you get this angle, then you'll have 2. And once you have 2 angles, then you can add them up and subtract from 180 to get the third one. And then once you finally get the third one, you can figure out this side. So that's the order of things we're going to do. First, do that second, and do that third. All right, let's start with beta. Okay, remember, every law of sines problem always starts out just like that. And how about Jack? Can you tell me what I could fill in on one side of this proportion using my information from the table?
Oh, you could put the 35.
Okay, so we could do sine of 35. Yep, divided by
6.
Perfect. So we're going to do sine 35 divided by 6. So he put all the known information on the left. So that means we're going to have some unknown information on the right. So now, what would I put on the right?
Sine beta.
Yep.
Under 8.
Sine beta over 8. And now, we want to get beta by itself. So we're going to start by just at least getting rid of the 8. So Abigail, what can I do on both sides to move this 8 over? Say it again.
Multiply.
Multiply, yeah, by.
Sine 35 over 6.
So yeah, we're going to multiply that by what?
8.
By 8. So we're going to move the 8 to the other side by multiplying by 8. That's gone. Multiply by 8. Don't worry about reducing that to 4 over 3 because we're going to type this in on the calculator. So it's not a final answer. So you don't have to reduce it if it's not a final answer. All right, it's 8 sine 35 over 6. That would give me the sine of beta. But my goal is to really get beta. So how are we going to get rid of sine? Yeah.
Arc sine?
Yep, I'm going to take the arc sine or the inverse sine on each side. Take the inverse sine of what's on the left. Remember, there's no multiplying, those parentheses don't mean multiply at all. The only multiplication in this problem is 8 sine 35, that's it. So we're taking the inverse sine of what's on the right, that's gone. And now we have a calculation we do for beta. All right, so type that in just the way you see it. Since you're typing in quite a bit, you've got to be careful with parentheses. Okay, let me show you how you put it in. So, inverse sine, 8 sine 35. You need to close the parenthesis because you're done with the sine. Now divide by 6 and close the parenthesis again because we're done with the inverse sine. And that's how you want to type it in, and that's what you should get, 49.886. So, this is not a no solution problem. If it was a no solution, we would have typed in something like this. We would have put the whole calculation in and we would have gotten an error. I didn't get an error here. So that means this works. So we need to write it down. 49.886. Okay. Any questions on how I just got that? All right, now think about this. 8 sine 35 over 6. That was equal to a sine function. Well, let's see what 8 sine 35 over 6 comes out to. So 8 sine 35 divided by 6. 0.76. The number itself isn't really important. What's important is that it's positive. You've got a positive number equal to a sine function. So now, think about this. Okay, we talked about this diagram, I think, before. You just got an answer in quadrant 1. You're looking for where the sine function comes out to a positive number. Where else does that happen besides quadrant 1? Yep. Yep, it's going to happen in quadrant 2. And think of that 49.886. This is like a reference angle. Does anybody remember what you do to get an answer in quadrant 2 with your reference angle? Yep.
180 minus the reference angle?
Yes. So this is the only case that you have to check for a second answer by doing 180 minus the reference angle. It's always 180 minus. It's never, you'd never have an angle in quadrant 3 or 4 because then that wouldn't even be a triangle. Triangles have to be less than 180. Okay. So let's check and see if we have a second answer. 180 minus 49.866. Wait, 886. So if there is a second answer, it's 130.114. I'm going to put that off to the side for a second while I think about it. That answer would have to fit in the triangle with the angle that's already given. How about, Ethan, what was the angle that we were given?
35 degrees.
We were given 35, and what do we think the second answer could be?
130.
130. If you add 35 and 130, is it less than 180?
Yeah.
Yes. Then that's how you know this problem has a second answer. Let's say the second answer came out to 160. Well, then if you took 160 plus 35, that's too big. Okay, but in this case, it's not. So, here's what's going to happen now. We're going to be solving two problems, two separate problems. We're going to use the same table to do it. If you want to make two separate tables, you could. But I think it's easier to just make one table. So beta is going to have two answers. If beta has two answers, then everything you're solving for has two answers. Don't worry about A, B, or alpha. Those were given. Those are done. But gamma, we don't know. And it's going to have two answers. And C1 and C2, we don't know. And that's going to have two answers. So now we're solving for 6 things. Two of them are done. So if you want to kind of think of it this way, if I color code it, the two problems, let's think of it as like the red problem and the blue problem. Alpha is an angle in the red problem. Beta 1 is in the red problem. Gamma 1 is an angle in the red problem. Those are the three angles that we're going to use in one of the problems. The other problem has alpha, beta 2, and gamma 2. Those are the three angles in the blue problem. So we have 3 red, 3 blue. Notice alpha's in both. Anything that's given to you is an angle that is shared in both problems. Do the same thing with the sides. A is a side in the red problem. B is a side in the red problem. C1 is a side in the red problem. There's your 3 sides for problem, the red one. A is in the blue problem. B is in the blue problem. C2 is in the blue problem. So there's your 3 red sides, 3 red angles, 3 blue sides, 3 blue angles. The red problem and the blue problem. 2 separate problems. With some information that's common to both. All right, let's look at gamma 1. What angles would I add together and then subtract from 180 to get gamma 1? Yep.
35 plus beta 1. And then you would take that and subtract it from 180.
Yep. So we're going to take the 35, because that's in the red problem, take the 49.886. And so far, for red angles, we've used up 84.886. Now subtract that from 180. And that'll tell you what gamma 1 is. 95.114. Now, you have enough information, you could go do C1 right now. But I like to just, if we're doing angles, I like to finish all the angles first. And then I'll go do all the sides. All right. How about gamma 2? What angles were we going to add up and subtract from 180 to get gamma 2? Yep.
35 and beta 2.
Yeah, the 35, that's a blue angle. And the beta 2, that's the other blue angle. Those are going to add up to 165.114. So subtract that from 180. 165.114. 180 minus 165.114. Okay, so that gives me 14.886. Each answer that we're figuring out would be worth its own points, okay, on the test. So, a problem like this might be a half a point for each one of those. And maybe this whole problem is worth 3 points out of whatever. Okay. All right, so we got 4 of the answers. Now we need to get C1. So, to get C1, we're going to have to set up the law of sines again. So let's do that. And C1 is part of the red problem. It's part of all the problem. It's part of the problem that has the ones as a subscript. Since C1 is part of the red problem, I need a full red row to fill in. What's a red row that I could fill in to my proportion? Zach, do you see a red row we could fill in? Yeah, Sarah?
A and alpha.
A and alpha. A and alpha is not only a red row, it's a blue row, so it works in both. So the other reason I would use that is because there's no decimals. Technically, B beta 1 is a red row as well, but it uses decimals, so let's stay away from it. All right, so let's fill in sine 35 over 6. And if we're going to find C1, what angle do I use? Chris?
Gamma 1.
Gamma 1. Sine 95.114 over C1. So let's cross multiply and divide. We'll do it all in one step. So 6 sine 95.114 divided by sine 35. And then close that last parenthesis. That's a little sloppy, but it doesn't really matter because I didn't type anything after it. So it's 10.419. Okay, so now we got C1. Now we'll set up law of sines one more time for C2. Alright, so that was C1 and C2. Okay, C2, that is a blue side. So can somebody give me a blue row that is complete that I can fill in? Oh, babe, you see a blue row that's complete?
Yeah, A and alpha.
Yeah, A and alpha again. You could use B beta 2, but you're using something that has a decimal, so it's going to throw the accuracy off of your answer. So let's do A alpha again. Sine 35 over 6 equals. And how about Jake, to find C2? What angle am I going to use?
14.886.
Yep, I'm going to use that gamma 2. So sine 14,886 over C2. Okay, so cross multiply and solve it. So you're going to do 6 sine 14, and then you're going to divide by the sine of 35. Any questions on how I'm doing the cross multiplying there? We did that last time, so I'm not focusing too much on it right now. So 6 sine 14, 886, and divide by sine 35. Might be quicker if you just pull up the last thing you typed in and just edit it, or you can just retype it like I did. So that gives me an angle of 2.687. Okay, and that's a 2-solution case. So that kind of problem, I mean, for me, I don't think it's harder, I think it's longer, because it's doing everything double. So you got to do it twice. So it definitely takes longer. Okay, any questions on any part of that? The order we did things in, how we got the second answers, angles, or the signs? Definitely, you will have a 2-solution one on the test. Definitely. Okay. So then let's take a look at this one. Now, I've always suggested the first thing you should do is figure out if this is a law of sines problem, because on the test they're all going to be mixed and they're going to be in random order. So you don't know if it's a law of sines or a law of cosines problem. You have to figure that out. Can anyone tell me, just by looking at this table, how do you know it is law of sines? If you don't know how to do it by looking at the table, you could sketch it. But that's going to take a little longer. Yep.
The bottom row's filled out.
Right. Anytime you have a complete row, that's law of sines. All right. Now, can somebody tell me what are you pretty much forced to find first? You don't have any choices here. Yep.
Alpha?
Yep. You have to find alpha first. And Casey, can you tell me how I would set this up to solve for alpha?
Sine 50 over C equals
And what's C? Since we know it, we'll fill it in.
1.
1. Yep, so sine 50 over 1. Good.
Sine alpha over
Sine alpha over, and what's A? 2. All right. So let's see if we can solve this and get an answer for alpha. Okay, now what would I do first there?
multiply by 2.
Yeah, you don't even have to really cross multiply because this is just a 1. All you have to do is if you multiply each side by 2, then you're going to have 2 sine 50. Don't worry about what that is, just leave it. And 2 sine 50 is equal to the sine of alpha. So Abigail, how would I get rid of the sine?
Inverse side.
Good.
Both sides.
Take the inverse sine on both sides. And does anybody remember when you take the inverse sine, you're always supposed to take the inverse sine of a number between these two numbers? Anyone remember what inverse sine is supposed to be between? Has to do with how high and low the regular sine graph goes. The range of the original and the domain of the inverse are the same. Yep.
Is it -1 or 1?
It's supposed to be -1 to 1. Well, if you type in 2 sine 50, you get 1.5. So if you try to take the inverse sine of 2 sine 50, it's not going to work, right? You're trying to take the inverse sine of a number that's too big, which means that there is no solution for alpha. You can't solve for alpha. And all three of these boxes have to follow the same pattern. They either all have no solution, they all have two solutions, or they all have one solution, and we did that one last time on Thursday. All right, so once you figure out that one of them is a no solution, there's nothing else you can solve for. You can't add alpha and gamma together and subtract from 180 because you don't know alpha. So there's no way to get beta. And if you can't find an angle, then it's impossible to find the other piece of information in the same row. Right? So they're all no solution. So what do you think would happen if you actually tried to draw this triangle? What do you think it would look like? You have a guess? Yeah?
Straight line.
Well, we're definitely going to have two sides. So because we have this side and we have this side, and we have an angle. So we are going to have two sides. But what do you think is going to happen with the third side? Yeah?
Is it just going to be a 50-degree angle?
So that would be part of it. So what I've done here is I drew a 50-degree angle. And then we have a side that's 1. What's the other side? 2. So an easy way to do that is just double the length of this. And now you have a side that's 1 and a side that's 2. Oh, almost. Close enough. All right. So we got a side 1 unit long and a side 2 units long. The side that's 2 units long is A. Well, in this diagram, A is the one that's tilted at a 50-degree angle. So that's pretty good. I can't change that. I have to keep this at a 50-degree angle. If I change it, I'm changing the angle. Can't do that. Now, side C is 1 unit long. That's where side C is going to be. They didn't tell you this angle. You can make it whatever you want. So you can swing side C out further. You can bring it in closer. You can do whatever you want with that side. So let me just make it so I can rotate it. Just a little trick so I can spin it. So there's your side C. And now the bottom is side B. Well, B wasn't given. That means do whatever you want with it. Make it as long or as short as you want. But it has to be horizontal. Because if it wasn't, you wouldn't have a 50. All right, so here's B. So the two things I'm allowed to change, I can make this side longer or shorter, and I can pivot that side closer in or further out. So if I'm allowed to do those two things, will it ever make a triangle? No. In order to make a triangle here, I would either have to be allowed to make this side longer, which would mean changing the information that was given. I can't do that. Or I would have to make this angle smaller, like tilt that bottom side up. But I can't do that either because it has to be a 50. So you'll never be able to get the sides to connect. That's what happens. Any question on that? That's an example, and that's all to scale. That is an actual 50-degree angle. It's all measured. That's perfectly to scale. All right. So last two questions we'll look at. These are the word problems. Now, before we even look at it, whenever they give you a lot of information in a word problem, what is it always helpful to do with all that information? Usually makes the problem easier to think about. Yeah?
Separate the information.
Do what?
Separate it, like pull out pieces of it.
Okay, so we're going to figure out important information from it. So maybe highlight or underline some important things. And what else is usually helpful with a word problem? Especially in trig, if it's like a problem about like a real world situation with like someone standing here and then you got a building over here, you know, things like that. What's kind of helpful to do? Yep.
Draw it out.
We're going to draw it up. Now, when we draw it, what shape do you think is going to come up in the sketch every time we do this? Yep.
Triangle.
We're going to get triangles. I don't want you to think about drawing a triangle. I want you to think about drawing the objects in the problem, and the triangle will just happen. Okay? All right. So the first one involves a surveyor measuring the height of an object in the distance. I think it's a mountain in this case. Yep, mountain. And basically what the surveyor is going to do is they're going to set up some equipment to measure the angle from where they're standing to the top of the mountain. That's actually pretty straightforward to do, especially if it's flat ground. You can set up what's called a transit, which is, you might, when you're driving, sometimes you see like a tripod set up on the side of the road, and then a little further away you see another one. People could be measuring the pitch of the road, they could be measuring property boundaries, but they're measuring something. Well, in this case, the surveyor is going to set up their equipment, they're going to look through it, they're going to sight the top of the mountain, and they're going to see exactly what the angle is, and their equipment will tell them that. Then, the surveyor is going to do it again. And the whole key is you're measuring the angle to the top of the mountain twice. And that's what's going to allow you to get the height of it. But you have to know how far apart each measurement was taken. That you have to know. So, you know, you've got your truck with all your equipment, you just set it up, take a measurement, and then just, you know, use the, you know, trip meter on your trucks, reset it, and then just measure how far you drive back and do it again. In this case, it's going to be a distance of 900 meters. Any distance will work. It just has to be known. So what is going to be measured each time is what's called the angle of elevation. Okay, the angle of elevation is basically an angle, like if I had a laser pointer, you know, and I had it resting on my hand, and I wanted to target, you know, the very top of the door. What angle would I have to tilt the laser at so it's pointing exactly at the top of the door? The angle between the laser and my hand, that's the angle that I elevated the laser. Okay. So the first time, we get an angle of elevation of 47 degrees. Now, if I had a laser pointer pointed at a target, and I start to back up, and I keep the laser pointed in exactly the same spot, what's going to happen to my angle? As I back away from a target, but I keep the laser pointed right at the same spot, what's going to happen to my angle? Because I can't keep it like this all the time and just walk wherever I want. It's always going to point at the same spot. I'd have to change this as I move. Yep.
It's gonna get smaller.
It's going to get smaller. Right? Think of like if you're watching a movie and you're in like a front row of a theater, think of the angle you have to look up at to see the screen. Well, if you move further away, you don't have to look up as steep. So your angle changes. Same idea. So the first time, the surveyor gets an angle of elevation of 47. As they back away from the mountain and measure again, they get an angle of 35. Now, what we're going to assume is that the transit or the device that they're using is level with the ground. Technically, that's not true. The transit would be on a tripod that's like 5 or 6 feet tall. So that would change it a little bit. But let's assume that whatever they're using is right on the ground, and they're pointing it from the ground to the mountain. Okay. All right, so we're going to take all that information and we're going to make a picture. And again, I want you just to think about the objects we're going to draw. So what's an object from this word problem that's very important to put in our picture? Yep,
Mountain.
the mountain, and even more basic than a mountain. What else do we need? We can't have a mountain unless we have this. Yep.
The laser.
Well, yeah, we're going to put that in too. That'll be one of the last things we put in, but it's even more basic. Because without this, you just have a mountain floating. Yes,
Ground.
you need the ground. All right, so we have nice level ground. So we're just going to draw in a horizontal line that represents the ground. Most of the word problems I give you are going to start with something like that. All right. Now I can put in the mountain that Eli said. So there's my mountain. And the surveyor takes 2 sightings of the peak. So let's say they measure something from here, and then they measure again from here. This is where the surveyor stands each time. How far apart did it say the 2 measurements were that the surveyor is going to do? Yep.
900 meters.
900 meters. And now imagine pointing like a laser each time from where the surveyor is standing exactly to the top of the mountain. Let me make that look a little bit better. That's just going to make it easier to look at. So let's put in a laser pointing right to the top of the mountain and do it again. All right. And the goal of what you're trying to find is this. That is the height of the mountain. Now I just need someone to remind me, the first time that the surveyor measures the angle of elevation, what did they get for the bigger angle? Yep,
47.
47? All right, so that is 47. Then they back up 900 meters, do it again. And what did they get that time? 30, what was it? Yeah,
35.
35. Okay, so I think we've labeled everything that we can. Questions on the diagram? All right, so let's trace a couple of the triangles. Let's start with this one. We have enough information to solve this triangle in red. That would be great, because then we're going to be done right away. Because H is what you want to know. Well, we know this is a 47. Do I know any of the sides in the red triangle? Okay, how about Matt? Do we know any of the sides in the red triangle? No. Well, that's a problem. If you don't know any sides, it's impossible to solve a triangle. Doesn't matter what law, what theorem you use. If you don't know any sides, you can't solve it. So for now, there's not really a lot we can do with that red triangle. We'll come back to it, but we're going to have to figure out something else first. Okay. Let's take a look at this triangle in black. Whoops. What happened? Let's fix that. Alright, so we know this side is 900. That's good. We know this is 35. Anything else that I know in that black triangle? Because the goal here is to know an angle and a side across from it. If we can get that, then we can do law of sines. Let's just keep writing down whatever we can. See what happens. Yep.
Can we get the bottom right angle?
Yeah. How would you get this angle, which is really this one right there?
180 minus 47.
Yeah. These two angles form a linear pair, so they make a straight line. So take 180 minus 47. So 180 minus 147, that gives me 33. Whoops, I meant 180 minus 47. Sorry, 47. 133. Okay. Anything else that I could figure out now? Even if it's not the height, is it just something else I could write down? Yeah.
You can figure out the other angle.
In which triangle? The red or the black?
The block.
Yep. I can get that other angle in the black one because I know 2 out of 3. And then, once I have that other angle, I will know an angle and I'll know the side across from it. Now you can do law of sines on the black triangle. Is that going to be the height of the mountain? No. But it could help you figure something out that could then be used to find the height. All right, so if we add these up, 133 and 35, what's that add up to? 168? So what does that mean this angle up at the top would be?
12.
12, yep. Okay. Now, remember the goal is to find the height of the red triangle, but what could I find in the black triangle that I could then reuse in the red triangle? Yeah.
The side across from 133 degrees.
So this side right here,
Yeah.
is that side part of the red triangle?
No.
So I agree you could find that side, it just will not help you at this point. Yeah,
You could find the side across from 35 degrees.
find the side across from the 35. Find this side. Because if you find the length of that side, which you can do in the black one, it's the same as the hypotenuse in the red one. They're the same side. And then you'll know a side in the red triangle. Finding the height's easy from there. All right. So let's call this side x. And let's set up our law of sines. So this side is also x. All right, so Abigail, could you tell me what I could put on the left to set up the law of sines to solve for x?
Sine of over 900.
Perfect. Sine of an angle, divide by what's across from it. So she put all the information that is known on one side. Now this side is going to have the unknown. So how about, Casey, what would I put on the other side?
Sine of x.
Well, remember, x is a side, so we don't want to fill in a side into a trig function.
So sine of 35.
Sine of 35, yep. And divided by
X.
x. Very good. So sine of an angle divided by what's across equals sine of an angle divided by what's across. So now let's solve for x, which is really the hypotenuse. All right. So x equals 900 sine 35. And then we're going to divide by sine 12. It's important you type it in just like that. All right, so that gives me 2482.88 for x. $24.82.88. Now let's fill that in right here. Now you've got a side in the red triangle. You don't have to use logs, sines, and cosines anymore. This is a right triangle. You can use Pythagorean theorem if you have enough information, which I don't think you do. You could use SOHCAHTOA. You could use log sines again, but it's kind of overkill for this. Okay, what I would do from here is solve it just like you're solving a right triangle. Look at your angle, and then look at your two sides that you're given. What position is side H in relative to the 47? Yep.
Opposite.
That's opposite. And what's the position of the 2,482? Yeah. It's your hypotenuse. And Francesco, what trig function involves those two? So do you remember the SOHCAHTOA thing to remember which trig function is which? So I don't know how far back it is. I mean, it could be like 15, 20 pages, because this was 3 chapters ago, so I don't know how far back it really goes.
It's far back.
Yeah, it goes pretty far back.
Is it cosine?
So cosine is when you know adjacent and hypotenuse, because that's the part of SOHCAHTOA. So we're looking at opposite and hypotenuse. Yep.
Sun.
Sine. So sine is opposite over hypotenuse. So let's write that down. Sine equals, and then fill it in. So Jack, what's my angle that I'm using here?
Hey, you're what?
My angle that I'm using?
Oh, 47.
47. So there's my angle. Opposite is H. H. And hypotenuse, 2,482. And Ethan, how would I finish up to get H by itself?
You would multiply each side by 2,482.88.
Yep. Multiply each side by the 2,482.88. All right, and that's 1,815.86. So 1815.86. And that's the height of the mountain. So, not a ton of steps, really. We just had to do log sines and then just set up this equation. So, all your work for this problem is what I just circled. It's not like it's 40 or 50 steps, but it's hard to sometimes get your diagram. And that's the whole key to visualizing it. That can be the hard part. All right. Any question on the height of the mountain? All right, so in this one, you had to find something else before you could actually find what they wanted. In the last one, you're not gonna have to do that. They're gonna ask you to find something, you're gonna be able to find it right away. All right, and this one is gonna be very similar to the last one in the sense you're going to have a stationary object and it's going to be observed by two different people. This time, the observers are going to be on different sides of the object. And what this is an example of is it's called triangulation. Okay, triangulating where something is, not necessarily how tall it is, but where it is, based on two people seeing the same thing. All right. So if you want kind of something to visualize because you're more of a, how could this be set up in the real world? You've got a boat out on the ocean, it's at night, and it has a light on top of it. And you can see the light, and your friend can see the light, and maybe you and your friend are 20 miles apart, and you want to know where the boat is. You can figure out exactly where it is, as long as you can see it and your friend can see the same boat. And you know how far apart you and your friend are. That's important. So that's all you need to know. So let's kind of look at what's going on here. So maybe the boat calls, maybe the two friends are represented by like Coast Guard stations, and the boat calls in because they need help. In this case, the two Coast Guard stations are 120 miles apart. And the ship, again, they turn on their light. Maybe they start flashing an SOS that they need help. Because obviously they could radio that they need help, but you can't necessarily tell where somebody is if you just get a radio signal from them. You have to be able to see where they are. And that's what the light is. So they turn the light on and each Coast Guard station sees the light. Now, as far as describing where the light is, okay, the way the Coast Guard station is going to do it is they're going to describe the direction they see the light coming from the boat as a compass heading. So let's say this is the boat. And the first Coast Guard station indicates that the direction to the boat is 40 degrees east of north. How do they know that? They can see the boat with the light on, and they have a compass. So they look at their compass, they look at where the light is, and they match it up. Like, okay, it's at a direction 40 degrees east of north. What does that mean? This is north. East of north is like to the right of it. That's what it means if the Coast Guard station is right there, to be 40 degrees to the east of north. That's the direction they see the boat. Now, the other station sees the boat west of north. That's the key that tells you that the Coast Guard stations are on each side of the boat. Right? It's like if somebody was standing here and looking at Chris, I would say, well, I see Chris right now to the left of me, but then if somebody's standing over here, they say, well, I see Chris to the right of me. So then that means there must be somebody on each side of him, in front of him, but on each side. Okay, so west of north, that would look something like, so you run the Coast Guard station over here. And of course, these directions are bearings that are relative to you, where you're standing. Okay, so where the Coast Guard station is. Okay, so that could represent whatever angle I said, 30, I don't remember what it was. I'm going to draw this nicer, but I'm just trying to give you an idea. Now, basically what happens is each one of these Coast Guard stations has line of sight on the boat. They can triangulate exactly where it is. And we know the distance between the two stations. So essentially, we're going to get a nice triangle right there. Again, I'm going to try to draw this nicer on the next page. But actually, you know what? I could basically just use that diagram. That works. So maybe I'll just stick with that. All right. So how far is each station from the ship? So the goal, by figuring out how far the boat is from each station, then the Coast Guard can set up a search area to find this boat. Because in real life, you're not going to get an exact pinpoint spot and be able to say the boat is exactly right there. Usually what they do is you have what's called there's an error. Not everything is perfect. So there might actually be a little bit of an error here where it looks more like this. They say, well, we know the boat is somewhere in that area. We don't know exactly, but we know that as you head further out, it's going to be somewhere in that area. And then this station could kind of do the same thing. They say, well, based on our equipment, we have a little bit of error, but we know the boat is like that. So essentially what you have now is something like this. You have a search area. So now what the Coast Guard is going to do is, depending on that type of search area, they're going to figure out how to search it. And if you Google like how the Coast Guard searches, it's pretty neat what they do. Like they have a very specific thing that they do to try to find an object like in the middle of the ocean. It's pretty fancy how they do it. But that's not really what we're getting into. And we're not going to have this uncertainty. We're going to have an exact pinpoint. So not quite realistic. This is more realistic. But that's also a little more complicated to figure out. All right. So I'll draw it again. So I draw it nice and neat, straight line, so you can see what's happening. All right, so the first thing we have here is we've got an object out in the ocean, and we have these two Coast Guard stations on land. So we should draw a line that represents water and ocean. In fact, you know what? Let's land. Okay, so we'll put Coast Guard station here. And actually, you know what? Since they give the direction is north, let me take this picture. And let's have the boat be above us. I think that'll make it easier. So here's your two Coast Guard stations. 1, 2. We've got our boat out there. And we don't know that the boat is necessarily, I'm just making my diagram a little smaller. We don't know that the boat is centered between the two stations. We just know it's out there somewhere. Let's put crosshairs at each Coast Guard station so we can kind of measure north-south. I know it's kind of hard to see it in the picture, but there's a line that represents north-south. And there's another one. So each Coast Guard station can see the boat. So let's put in, this might be easier to see. There you go. So they have a line of sight to the boat, and so do they. And again, we don't have any error. Real Coast Guard, they're probably going to have a little bit of an error, which is going to be a big area to search. We've got an exact pinpoint. Not realistic. All right, this is north. North. Can somebody tell me what was the angle that the first Coast Guard station saw? I know they were 120 miles apart. But what was the angle east of north for the first Coast Guard station? Yep.
40 degrees.
40? And was the other one 30 degrees west? Okay. And which Coast Guard station was which? Z is west of X-ray. So here's station Zulu. I could just name them. Zulu's over here. x-rays over here. And now it's just a matter of finding the distance of each side of that triangle. All right, so let's take that, just take it out of the picture and fill it in. So this side is 120. What's that angle right there? Yeah, that angle's 50. I don't really care about the angle outside the triangle. I need the one inside. How about that one? Yeah, 60. Now, how about that one? Because the key is I need the angle across from the side that I know. Yeah, 70, because they all have to add up to 180. So now, let's just call this A and B, and let's set up an equation, and we can find both of those directly. So, can someone give me the piece of information that I can use to find A and to find B? Yeah,
Sine 70 over 120.
that's the whole key to both parts. Sine of the angle divided by what's across from it. Let's do it for B. And now I want to find A. So what angle am I going to use to find A? Yeah. 60. Always use the one that's across. Sine 60 over A. Okay, we'll solve that in a second. And what angle am I going to use to find B? Yep, 50. Use the one that's across. And that would tell you, if you were drawing these lines on a map, like if this was all really to scale, exactly the coordinate of where that boat is. Of course, if the boat's moving, that makes it more complicated, but we're just assuming the boat's going to stay still. All right, so let's figure out the distance from, what's A? That's from Zulu to the boat. All right, so 120 sine 60. Sine 60. Yeah, we're going to divide by sine 70. So that one's 110.6 miles. So if you don't have equipment that can go that far, well, then sending a rescue from that station is out of the question. Let's look at B. So B is 120 sine 50. And now you're going to divide by sine 70. 97.8, so they're a little closer. But who knows, if just because they're closer, that doesn't mean that's the one they're going to send out. Maybe there's a storm and the winds are blowing 50 miles an hour in the direction of station B. So for them to send a helicopter from there, it's going to be pretty rough. So maybe A would make more sense. But anyway, we know where the boat is now, so we can decide to do whatever we want. Any question on that? Has anyone ever been to Mesquamaket Beach? In Rhode Island? No? Oh, that's the beach I used. It's in Rhode Island. Nice beach. All right. All right, so those are the questions for tonight. Okay, don't get discouraged if you get a no solution answer. It doesn't mean you're doing it wrong. You could. In fact, I think there's at least 2, maybe 3 problems that are no solution.